Waves. In this video series, we are going to dive deep into waves and see how really waves work. And physics behind waves are going to be explained in this video series. So, what really waves are and why do they really matter? So, waves matter, guys, as waves transfer energy from one point to another point. For example, you can hear me as the energy created by myself. I put some energy to talk. So when I speak, my energy is transferred to you. That's why you can hear me through sound waves. This energy is transferred. So, but how about matter? Do matter transfer with waves? We dive deep into these concepts. Keep in touch. Right. Take a look at this simulation, guys. Now here I'm going to show you how waves propagate in a medium. So I'm going to generate a simple wave like this, right? Make sure the wave propagates smoothly in the medium, right? Can you see that particles are just moving up and down? They don't really uh, move along with the wave, even though the wave propagates in the medium. So it's crystal clear that particles are undergoing or executing a simple harmonic motion even though the wave propagates in the medium. So I'm going to change the motion pattern, right? So instead of vertical displacement, this time I'm going to give a little horizontal displacement like this, right? But a wave shows up still. There's a wave in the medium, but there's a little difference this time. Instead of the vertical uh, simple harmonic motion, we can see now horizontal oscillations throughout the region. Right now, I really want to introduce a few wave properties which dominate and which govern this entire lesson. Let's quickly go ahead and understand what really a wave is. A wave is a disturbance in a medium that carries energy without a net movement of particles. Right. So, as mentioned in my definition, right, the waves carry energy. So, simply waves transfer energy through a medium, but there's no net movement of particles. But particles are moving, so they are simply undergoing a simple harmonic motion or simply an oscillations. They're undergoing oscillations. If you don't really know what the simple harmonic motions are, I will explain those things in it for. Don't worry. So just keep that in your mind. So just a simple harmonic motion, right? And then wave properties, right? So now there are some very important wave properties. If you really want to grasp some of the wave concepts really well, you need to know these concepts in advance. So I'm going to explain all the wave properties now, and let me quickly walk you through all of those wave properties. Very first wave property is displacement. Imagine a string. When the string is at rest, so there are a few, and this green color string is at the beginning it's at rest, and there are some right, so I'm going to consider a few particles. Oh, anything, particles or any sort of um, joins or anything as you wish. So now I'm going to make a wave. Right, now I'm going to generate a wave. uh, so here I'm going to connect this left corner or the left end of the string to a vibrator, and now this vibrator is going to generate a wave. Right, then I'm going to take a snapshot of, now this is a wave, right? So as you can already see, there's a wave. That's a wave propagating in the medium. And now this is just a quick snapshot of the wave, right? And I'm going to see where the particles really appear now. So they are no longer uh, at this level anymore, right? So these particles must have moved away from the initial position. So this level is always called the equilibrium level, as particles were at rest at the beginning. So this is the equilibrium level. So now you can find out. So let me label these particles. So this is my particle A. Oh no, I need A for something else. So this is my particle P, Q, R, S, T. Right. So those are the particles. Now, uh, the new position of the particle P is no longer this position it where previously the particle was existing. Now it is somewhere here, right? This is the new position of the particle P, right? This is now where you can find the particle P, right? And the Q particle is no longer at this level, and this is where you can find the Q particle. So R particle is no longer at that place, so this is where you can find the R particle. So even S particle is now at this place, and T particle is at this place now, right? So now the displacement from the equilibrium level is what we usually measure as the displacement. Simple as that. So let me consider the displacement of this particle is now x1, and this is x2, and this is a special displacement, so I'm not going to label this, as I will need this displacement later on. I'm going to use this displacement later on for something else. And this is my x3 displacement, and this is x4, right? So the particles, now you can see all of these displacements, right? Now if this is the displacement zero level, right? If you consider upward direction the plus direction, then uh, naturally or automatically downward direction or downward becomes negative. So now you can see that this is the only negative displacement you can find out here. This is something minus, but I'm going to introduce this as minus A, because this is special, because it's going to connect to the next important lesson, which is amplitude, right? As amplitude is the maximum displacement obtained by a particle in a medium where um, a wave is propagating, right? So wave is moving. So now here you can see that among all the other particles, this capital R particle, yeah, the direction is negative, but still it has obtained the maximum displacement, right? So that maximum displacement is amplitude, right? So then here the magnitude of the maximum displacement reached by an oscillation in the wave is called the amplitude. It doesn't matter what the sign is, it can be either negative or positive, but the magnitude matters, right? The maximum magnitude is the amplitude, right? That's it. Right, and the next important term is period. Right, so there are two different ways to define the period. So this is the very first definition of period. Period is the time taken for one complete oscillation at one point on the wave. Right, actually, how could this be possible? Right, now imagine this is the medium where a wave is propagating, right? Now this is a single wave cycle. Don't ever forget, how a single wave cycle looks like, right? So this is how a single wave cycle looks like, right? I'll draw it again. It's not that cool, right? So this is a cool single wave cycle. Right now, there's a particle. Now, this wave is about to pass through this point. So this is my point, whatever it is. Just mark this point as yep, Q point, right? So now when this wave cycle completely passes through the Q, right? So the new position of the wave would be like this. This is where we can find the new right, when the wave completely gets through this cycle, sorry, particle Q, right? So the new wave will appear like this, and it has already passed through the Q point, right? The time taken for this wave cycle to pass through this point is the period. So that's the second way of defining this same term, which is period, right? So it's a time, just the time taken for a single wave cycle. That's the second definition, right? I will write the second definition to make it clear. Now the clear second definition that you can write down anytime you want is time taken by a single wave cycle to pass through a point yeah, that's it, through a point is called the period. So that is also a correct definition, right? The next important term is frequency. So how can we define frequency? There's a very close relationship between frequency and period, right? I'm going to define, or I'm going to say you later on what the relationship between these two terms is. And the frequency is the number of complete wave cycles per second, right? So I'm going to tell you another way better definition, so even this is okay. Frequency is the number of complete wave cycles per second. So just as our previous case, just try to relate these two. Now the previously period was the time taken for a single to complete a single wave cycle or single oscillation, but here it is frequency is the number of complete wave cycles per second or number of oscillations per second, right? So rather than this, I can say that imagine number of wave cycles passing through a point per second, right? So now this is a single wave cycle, so we identified this as the time taken by a single wave cycle to pass through a point, but now this time it is number of wave cycles pass through a point per second is called the frequency. And the relationship between frequency and time period is frequency is equal to 1 over period. You can use this relationship anytime. It's a ready-made equation that you are totally free to use anytime you want. So just keep it in your memory, as this is very, very useful. So another alternative unit that you can use to measure frequency is, now you already know the period is measured in seconds. So we already know the unit of frequency is hertz, but so per second is also a relevant unit in terms of basic units, right? Super cool. Then there's one missing term I really want to introduce to you, which is wavelength, right? Even though wavelength is not here, Just I think you will be able to manually write this note, right? I will encourage you to take this down, which is wavelength. Wavelength, right? What is really wavelength? Okay, now later on we'll come across a very important lesson, which is phase angle, right? So we refer to phase to describe what the wavelength is, but till then I'm going to use this definition. Even this definition is totally fine, it's totally correct. You can even use this definition to describe what really the wavelength is. So wavelength is, now imagine, right, I'm going to draw a wave again, and yeah, this is my, yeah, first wave, and there's another wave. Now you can see two wave cycles here, and this is my first wave cycle and this is my second wave cycle, right? Let me separate these wave cycles properly, right? And wavelength can be defined as distance between a point on a wave cycle and the same point on the next adjacent wave cycle. Distance between, okay, I'll write it out. You can also take it down if you want. Wavelength is the distance between one wave cycle and, oh sorry, my bad, distance between a point on one wave cycle and the same point on the next adjacent wave cycle, right? Okay, now yeah, these two are corresponding or identical points, so this distance between these 2 points must definitely be the wavelength, which is lambda. And even in IGCSE, you must have learned what this point is. This is a crest, right? Even this point is a crest, and this is the crest on the very next wave cycle, and this is a trough. Even this is a trough, but this is the trough on the very next wave cycle. So even the distance between these 2 points is equal to the wavelength, right? That's fine, right? Right, and the next important term is wave speed, right? The rate of movement of wave. You already know what the speed is. Speed defines the rate of movement of something, right? So how fast you are, just as that wave is something moving. So you can even figure out the speed of the wave, right? And yeah, I can use a better way of finding the wave speed, right? Okay, now let me refer to two of the previous relationships. Right now, v is equal to right, the speed of something, as we already know. The speed is equal to distance over time, which is not a strange relationship. And now, uh, can you remember what we have come across here? So we came across that the time taken for this single wave to pass through this point is capital T, which is period. So I can say that I can use that relationship to right? Something about speed. Then, and we already know the length of this wave is wavelength. Now here to there, and this is the starting point of the wave and this is the ending point of the wave, or you can say the starting point of the very next wave. So the length between these 2 points is equal to wavelength, right? So the distance traveled during the period of time is wavelength over period, right? And now I'm going to modify this equation a bit. So this is lambda times 1 over t, right? So 1 over t is equal to the frequency. So as we have already come across that f is equal to 1 over t, so I can replace 1 over t with frequency. So I end up getting one of the important equations. This is a very, very important equation. We will come across this equation every time later. So you need to really know what this equation is. So it is v equals f lambda, right? Just highlight this equation. It's been already given here. Right, now it's high time to do some questions. These are not really complicated questions. You can easily figure out what these questions are trying to say. So I would like you to give this a try. So yeah, you can pause the video and read these questions and give this a try, and then uh, you can play the video and watch how I'm going to do these questions, right? Okay, now read the very first question, Kel. It's very easy question. It's a very simple one. A period of oscillation of a particle in a medium where a wave is propagating is 0.25, right? So we already know the period of this. So now therefore you can easily find what the frequency is. Can you remember the equation that we came across is f equals 1 over t, so is equal to 1 over 0.25, right? So then 1 over 0.25 is equal to 4 hertz. So the frequency of this wave is 4 hertz. Then find the wavelength of the wave if the speed, right? So now we can plug this into v equals f lambda relationship. Just substitute v is equal to f lambda, and v is 12.5, and frequency is known, which is 4 times wavelength is lambda. So now lambda is equal to 12.5 over 4, right? Now it's you can simplify this and find out the final answer, which is 12.5 over 4 is equal to 3.125. 3.125 meters is the wavelength of this, right? Right, so let me quickly walk you through question number 2. Question number 2 is a wave has a frequency of 50 hertz and the wavelength is 10 meters. What is the speed of the wave? It's a super cool question. You can easily find the answer. So now v equals f lambda, and v is already been given, which is 50 and lambda is 10. It is 500 meters per second. Simple as that. Right, now example number 3. Okay, question number 3 is a water wave is traveling with a speed of 0.6 meters per second in the positive direction, right? So it's moving in the positive direction as shown in the figure. Find the wavelength of this wave, hence find the frequency of the water wave, right? Now find the wavelength. Right now you can clearly see that this axis shows it's a distance versus displacement versus distance graph, and this y-axis represents the displacement. In the meantime, x-axis represents the distance. This is a quick snapshot. So wavelength is from that point to this point. So this length is the wavelength, which is 0.2 meters. Right, find the wavelength, and lambda wavelength is 0.2 meters. Right, and then a frequency of the water wave. Right, then you're supposed to find the frequency of the water wave, which is not directly being given, but we can use v equals f lambda relationship to find the frequency of this. Right now v is 0.6 meters per second, and f is what I'm looking for, and this is 0.2. Move this to other side, then f is equal to 0.6 over 0.2. It makes sense. 3 hertz is the frequency of this wave. Right, that's fine. Super cool. So what is the amplitude of this wave? You really don't want to find this. You really don't want to use any math relationship to find the amplitude of this. It is, yeah, it's directly visible, which is 0.5 meters is the amplitude, as that's the maximum displacement obtained by any particle, right, in the medium where wave is propagating. So it is 0.05 meters. Right, that's it. Right, then how will the wave appear if period of the wave increases? Right, so you need to understand now the period is going to be increased. So but there's one important point, guys. The wave speed, right, most of the time students are confused. I have seen this. So they can't figure out sometimes that the factors affecting the speed of a wave, right, speed of the wave, right. So now, but yeah, so they conclude it based on v equals f lambda relationship sometimes, and according to this relationship sometimes they naturally tend to think that speed depends on frequency and wavelength, but that is not really correct, guys. Always remember, wave speed depends on the nature of the medium. For example, the wave speed of the not wave speed, just consider the speed of sound in air. It depends on the temperature and the molar mass of the gas, right. So molar mass of the gas or whatever the medium where the wave is traveling. So just as that wave speed, if unless you change the nature of the medium, wave speed remains constant. So frequency and lambda in the sense, now if you move the frequency term onto the other side, so if you move this to this side, so lambda equals to v over f in the sense, now lambda and f are kind of inversely proportional to each other. So in the sense, if you change or if you increase the frequency, wavelength decreases, right. So now, and how about period and the frequency? You already know the frequency is equal to 1 over t. So when they are also inversely proportional to each other. So if the period of the wave increases, if you increase the period of the wave, frequency of the wave decreases. So as the frequency of the wave decreases, wavelength of the wave increases, right. So now wavelength of the wave is higher than the previous wavelength. We don't know the proportion of that reduction, but it doesn't matter, as magnitude is not my concern. you can just draw the new wave like this. It doesn't matter what the amplitude is. Even you change the amplitude, I'm totally fine with that, as you can't directly find what's really going on with amplitude here. So just make sure you write a wave with greater wavelength. This time the wavelength should definitely be higher as the frequency gets lower. Right. Wow, that's nice. Right, so we now dive deep into the wave classification, right? So there are uh, two different ways. That brings us to the end of this video, which is the first chapter of this video series. In this video, we went through all the key properties of waves: displacement, amplitude, period, frequency, wavelength, and wave speed. In next video, we will dive deeper into wave properties. See you there.